May 1943, Central Germany, Dessau Airfield. A test pilot stands before an aircraft that will define the limits of human ambition. But here's the question no one wanted to answer. What happens when you build the future with materials from a collapsing empire? Inside a reinforced hangar, designed specifically to contain engine explosions, Hans Werner Lucht approaches a modified Messerschmitt 110 fighter. The aircraft rests on wooden blocks, its fuselage stripped bare, exposing the machine's mechanical skeleton. The war, already lost, though not a single German official will speak those words aloud. American bombers are systematically erasing German industry from the map. 800 aircraft per month. The Luftwaffe bleeds pilots faster than training schools can produce replacements. And into this maelstrom of industrial collapse, German command has placed all remaining hope into two gleaming objects mounted where conventional engines once sat. Two Junkers Jumo 4 turbojet engines, the world's first production jet engines. Under harsh work lights, they represent either the future of German air superiority or the most spectacular symbol of industrial failure the 20th century would ever witness. But which one would it be? Lucht is 31 years old. He's tested captured American fighters. He's flown 60 different aircraft types. He understands engines the way master architects understand load-bearing structures, instinctively, completely. The Luftwaffe command has given him one impossible mission: fly this jet-powered aircraft and discover what's killing it from the inside. He has one day, because by May 1943, everyone in that hangar knows the same uncomfortable truth. The technology is revolutionary. The reliability. Catastrophic. 200 Me-262s sit in production facilities right now, waiting for engines that factories cannot deliver fast enough. Aircraft of the future grounded by the physics of the present, Lucht climbs into the cockpit. He knows that above 8,000 feet in the thin, cold air where engine temperatures climb toward 900 degrees Celsius, something fundamental is breaking. The briefing was clinical. The reality will be different. The prototype Jumo 4A engines demonstrated 100 hours of running time during bench testing. 100 hours of reliable, revolutionary performance. But those engines required materials Germany can no longer obtain. Nickel, cobalt, molybdenum, all now rationed to artillery production and tank armor. So the production version, the 4B, has been redesigned. Same power output, cheaper materials. One critical trade-off that no engineer wanted to make. Time between overhauls dropped from 50 hours to 25. Think about that number. 25 hours. That's barely one day of continuous operation before the entire engine requires complete structural overhaul. Lucht has 45 minutes of fuel. 45 minutes to understand why the most advanced engine in German aviation can only run for 25 hours before structural failure becomes inevitable. 45 minutes to discover if Germany has created the future of air warfare, or if they've created a beautiful machine that will kill its pilots faster than they can train replacements. What would you do with 45 minutes to solve an impossible problem? The Me-110 screams down the runway. Dual engines at full throttle. Lucht feels the vibration immediately, not the rhythmic pulse of a piston engine, something different, something alien. A cascading wave moving through the airframe like an invisible earthquake. The Jumo 4 has a problem no one in the Luftwaffe wants to acknowledge. It's disintegrating while running. Dr. Anselm France at Junkers designed the 4, a genius engineer who created something technically revolutionary. An 8-stage axial flow compressor. A single-stage turbine. Fuel injectors that could atomize kerosene into a combustion chamber running at temperatures that would melt conventional aircraft engines. Revolutionary? Absolutely. But here's what the textbooks won't tell you. The cost of this revolution is measured in hours, not hundreds, not even 50. 25 hours, that's the official time between overhauls. The time at which turbine blades begin catastrophic failure. Lucht banks left, climbing toward 15,000 feet. The vibration intensifies. He feels it in the control stick. A flutter, a hesitation. The compressor blades are responding to resonance frequencies the engineers never anticipated. Can you hear it? That high-pitched whine that tells you something is fundamentally wrong. The German engineers made a fatal calculation. When they redesigned the 4B for mass production, they had to eliminate scarce materials. The original prototype used nickel, cobalt, and molybdenum, strategic materials Germany no longer possessed. So they switched. Mild steel. Chromadur, a chromium manganese alloy developed by Krupp. Folded and welded turbine blades cooled by compressed air bled from the compressor itself. The mathematics, elegant. The metallurgy, clever. The reliability, approaching zero. At 18,000 feet, Lucht levels off. The vibration is now a constant tremor running through the aircraft like a living thing. He watches the engine temperature gauge. The needle climbs, 850 degrees Celsius, 870. The turbine blades are being cooled by compressed air that is itself being heated to extreme temperatures. It's a system balanced on the edge of catastrophic failure, and Lucht can feel that edge in every movement of the control stick. Here's what makes the Jumo 4 design revolutionary: its elegant simplicity. An 8-stage axial flow compressor that takes air at 400 mph and compresses it to 4 times atmospheric pressure in a space the size of a man's torso. The compressed air enters a combustion chamber where atomized fuel ignites at temperatures reaching 900 degrees Celsius. The exhaust drives a single-stage turbine connected by a common shaft back to the compressor, creating a self-sustaining cycle. The efficiency, remarkable. The power output, unprecedented. The structural stress, approaching the material limits of every single component. Lucht engages his timer. He needs to understand this problem during flight, while the engine is under stress, while the resonance patterns are active. But here's the question that haunts him. Why didn't the Americans face this problem? The American approach was fundamentally different. They designed their Allison engines with a time between overhauls of 500 hours. Not all at once, they could maintain an engine through months of continuous operations. The German calculation had been inverted. Maximum power. Minimum materials cost. Maximum speed toward operational collapse. The vibration begins to change character. Where it had been a flutter, it becomes a series of discrete pulses. The turbine blades are entering a feedback loop with the combustion chamber. Each ignition cycle pushes the blades toward resonance. Each resonance cycle destabilizes the next ignition. The engineers at Junkers switched from exotic alloys to chromadur, using only 12% chromium, 18% manganese, and 70% iron. Common metals that Germany could still produce in quantity. But chromadur was softer than the original nickel-cobalt alloys, more susceptible to fatigue. It couldn't handle cyclic stress the way advanced metallurgy could. Lucht can visualize the physics without seeing the metal. The thin chromadur blades, welded at the roots, cooled by air moving through at speeds approaching 600 mph, beginning to fatigue. Each combustion pulse creates a stress wave. Each stress wave creates a microfracture. Each microfracture reduces the blade's resistance to the next pulse. It's a cascading failure mechanism, not a question of if the blades will fail. Only when. Below him, the German landscape stretches out in spring sunshine. He can see the industrial heartland, the factories producing these engines. How many other test pilots are at this exact moment discovering the same fundamental truth? The technology is incredible. The ability to sustain it is measured in hours before blade fracture becomes inevitable. Lucht maintains altitude at 18,500 feet. The engines are at sustained power now. The vibration has become almost musical, a high-pitched whine that penetrates the entire airframe. He understands what's happening. The turbine blades oscillate in a resonance pattern their welded roots cannot absorb. Each cycle causes microfractures in the weld lines. The chromadur metal, strong under steady-state heat, is becoming brittle under cyclic stress. The Americans understood something about mass production the Germans were learning too late. You can design revolutionary technology, but if you want it to survive beyond the laboratory, you have to give it margins. Safety margins. Material margins. Time margins. The original Jumo 4A had been tested for 100 hours on the bench. It demonstrated reliability across its complete operating envelope. But it required materials Germany was rationing to the armaments industry. Nickel from Romania, cobalt from Central Africa, molybdenum from Scandinavia, all now allocated to weapons production. In 1943, the Luftwaffe command faced an impossible choice. Continue with the 4A, producing perhaps 50 engines per month using scarce materials that could be spent on artillery, or approve the 4B redesign, allowing mass production of 200 to 300 engines per month using common metals. The cost would be measured in durability. The 4A had a time between overhauls of 50 hours. The 4B would have 25. This wasn't a design flaw. This was an economic calculation. What would you choose, quality or quantity? Dr. Anselm France and his engineering team made a heroic effort. They designed a combustion chamber using 6 flame tubes instead of 8, reducing pressure oscillations causing blade resonance. They introduced a variable geometry exhaust nozzle that could adjust the jet exit area based on engine speed. They implemented a fuel injector system to stabilize the combustion process. All these innovations reduced the resonance problem, but they didn't eliminate it. In the design specifications, the 4B was rated for 25 to 35 flight hours before structural overhaul became necessary. Lucht begins his descent. He's been aloft for 32 minutes. The fuel consumption of the Jumo 4 is astronomical compared to piston engines. The engine burns 3,680 pounds of fuel per hour at cruise speed. A piston-powered Mi-110 burns 240 pounds. The jet engines consume fuel 15 times faster. The trade-off had been speed, incredible speed. The Mi-262 could fly at 540 mph while piston-powered fighters struggled to reach 380. But at what cost? Fuel capacity. The Mi-262 carried 2,470 liters of fuel. A piston-powered fighter carried 300 liters, 6 times less. This meant range was severely limited. Every combat mission would consume fuel at a rate requiring refueling after just 2 hours of operation. His port engine temperature reads 885 degrees. The limit is 900. Beyond that, the chromodur alloy begins losing its hardness. Beyond that, the welded roots can no longer support the centrifugal forces on the spinning rotor. He's approaching the edge of the safe operating envelope, and he still has minutes of flight remaining. The mathematics of the situation becomes crystalline. The Jumo 4 is not an engine designed for sustainable operations. It's an engine designed for desperate situations. Maximum performance, minimum durability, perfect for a nation fighting for survival, catastrophic for a nation trying to establish air superiority. The descent to the airfield is the critical phase. Lucht must maintain engine power. He must manage the cooling. He must land an aircraft with engines that are fundamentally unstable. One mistake in the landing approach, one hesitation in throttle management, and both engines could flame out. Or worse, a turbine blade could separate and penetrate the fuselage. He lines up with the runway. The vibration is now almost unbearable. The engines have been running for 38 minutes. In the design specifications, they still have another 12 hours before overhaul would theoretically become necessary. But Lucht can feel the clock running differently. The vibration is telling him the engines are living on borrowed time. The engineers had been optimistic about the 25-hour calculation. They assumed perfect conditions, perfect fuel flow, perfect cooling, perfect handling. But when has war ever been perfect? Lucht is not flying under perfect conditions. He's at high altitude. He's pushing the engines toward their thermal limits. He's discovering that the real-world service life of the Jumo 4 will be considerably shorter than theoretical calculations. In combat conditions, with pilots forced to maintain power settings to escape enemy fighters, the engines would be living hours, not days, before catastrophic failure. The landing gear comes down. The aircraft settles onto the runway. Lucht deploys the dive brakes to increase drag. The wheels touch concrete. The engines are still running. The vibration is still present. He rolls to a stop in front of the hangar. The engineers are waiting. Lucht climbs out of the cockpit and walks directly to the debrief room. He's been in the air for 42 minutes. Both engines are still running. Neither experienced catastrophic failure, but both demonstrated the fundamental problem that would define the Jumo 4's operational life. The data is clear. The vibration profile indicates turbine blades resonating at frequencies between 2,500 and 3,200 cycles per minute. The compressor rotor is oscillating in response to combustion chamber pressure pulses. The metal isn't fracturing yet, but it's fatiguing. The fatigue curve for the chromodur alloy shows that at current stress levels, the welded blade roots will reach critical fracture threshold at approximately 25 to 35 flight hours. The calculation is simple, brutal, unavoidable. A single Jumo 4 engine running at design power settings in operational conditions can sustain continuous operation for 25 hours before structural failure becomes inevitable. A German fighter pilot in sustained combat operations could expect an average engine life of approximately 10 to 15 hours. Why? What makes combat so destructive? Because combat requires sustained high-power operations. Combat requires maneuvers that push engines toward their thermal limits. Combat means continuous throttle adjustment that destabilizes fuel flow and increases resonance effects. By contrast, the American Allison engines powering the P-47 Thunderbolt and other fighters were designed for service lives exceeding 500 hours. Some were rated to 1,000 hours before overhaul. The mathematical difference isn't just engineering preference. It's a fundamental difference in industrial philosophy. The Americans could afford to design engines with massive safety margins because they had the raw materials. The Germans could not. They were rationing every ounce of strategic metals, so they designed for minimum weight, minimum materials cost, maximum thrust. and maximum failure probability. The contrast is absolute. 25 hours versus 500 hours, a 20-to-1 difference. An American pilot could fly 40 sorties before overhaul became necessary. A German pilot could fly 5. Think about what that means for the air war. The mathematics of industrial production was now the mathematics of air superiority. When Lucht delivers his report, the reaction is silence. The Luftwaffe commanders understand the implication. The Jumo 4 represents the future of German aviation, but that future lasts only 25 hours before the turbine blades begin to fail. They could continue development, they could pursue better materials, they could attempt to improve the resonance characteristics, but all those improvements require either time or resources. Germany has neither. The solution is technically possible. Anselm France and his team could have continued the original approach. The 4A demonstrated 50-hour reliability, but it required metals now being allocated to tank armor and artillery shells. Choice is immediate. Either divert strategic materials from ground weapons to aviation engines, or accept that jet aircraft can only sustain operations for days, not weeks. The Luftwaffe command chooses neither option. They choose to proceed with the 4B and hope that combat conditions will somehow be more forgiving than test flight data suggests. How do you think that worked out? Lucht understands what has happened. This isn't a failure of engineering. This is a failure of industrial capacity. The Germans have invented the jet age, but they've entered it with an economy that's already collapsing. They can build revolutionary aircraft. They cannot build the engines to sustain them beyond weeks of operations. The Mi-262 production rate accelerates. By August 1944, 91 aircraft are delivered in a single month, but the Jumo 4 production rate cannot keep pace. The factories produce 50 engines per month. The airframe factories need 200. This shortage becomes the strategic bottleneck. Germany built roughly 1,433 Mi-262 airframes during the war, but fewer than 300 ever flew in combat. The rest sat incomplete, waiting for engines that never arrived, waiting for turbines being manufactured as fast as the German industrial system could produce them, waiting for components that had to balance two impossible requirements: sufficient power to overcome Allied air superiority and sufficient durability to survive long enough for the investment to be justified. By August 1944, when the Jumo 4B finally enters operational service on the Mi-262, the data hasn't changed. The engines still have a time between overhauls of 25 hours, but improvements have been made. The engines can now sustain 20 to 25 hours consistently. This represents a marginal improvement over the 10-hour average of earlier production batches. Pilots still have to accept reality. Every flight pushes their engines toward inevitable failure. The only mitigation? Design maintenance procedures that can complete overhauls quickly. Train mechanics to replace engines and turbines in hours instead of days. Except that the Jumo 4 is not an engine in the traditional sense. It's a consumable component, an expensive, high-performance consumable that needs replacement after every 25 hours of operation. This is the lesson Lucht carries back from that May 1943 flight. Revolutionary technology can emerge from scientific genius, but sustaining that technology requires industrial resources Germany simply does not possess. The 25-hour limit is not a failure to be solved. It's a structural reality imposed by the material conditions of the war. Hans Werner Lucht survived the war. He lived until 1993. In his later years, he wrote extensively about his test flight experiences. He never publicly criticized the German engineers or the Luftwaffe command. But the fact remains, the Jumo 4 represented the highest point of German aviation technology, and it was fundamentally limited by industrial constraints that no engineering genius could overcome. The contrast is clear. An American Allison engine running 500 hours. A German Jumo 4 running 25 hours. The difference wasn't German incompetence. The difference was American industrial capacity. By 1943, Germany was running out of raw materials needed to sustain advanced manufacturing. America was at peak production. And here's the truth that decides wars. The air war that followed was not a contest of pilot skill or aircraft design. It was a contest of industrial mathematics. And on that mathematics, there was only one possible outcome.